Carlos, maybe we should start.
Okay. All right. All righty. So I think we're ready to for business now. So yeah. So it's a pleasure for us to have today one of our own, George Zahariade. In particular because it's a special topic in the sense that this part of this work has been awarded the first place in the sense of how this is called it was awarded first place in this 2020 essay competition of the Gravity Research Foundation. Um, so we are looking forward to hear about it. I want to welcome everybody which is outside from ASU and thank everybody for joining us today. And without much further ado, I think we are ready to start. So thank you, George. Please go ahead.
Thank you, Carlos. Yes, so thank you for giving me the opportunity to give this first Zoom talk. It is my first actual real scientific Zoom talk, so we'll see how it goes. But yes, I'm also excited to talk about this topic because it's the first time I talk about this topic, and it's work that I have done with Malik Parikh and Frank Wilczek at ASU here for basically the past 2 years. So it's kind of nice to have something a little bit more rounded to talk about. Okay, so the title of my talk is Quantum Mechanics of Gravitational Waves. And in this work, what I'm going to talk about is the interaction between a quantized gravitational wave and a gravitational wave detector, which will be basically a model for the arm of a gravitational wave interferometer. And I want to stress from the get-go that the way we discuss this problem is very conservative in some sense. What I mean by this is that we do not use any techniques that are beyond standard quantum mechanics and quantum field theory and general relativity. Okay, so let us start. Let me see. Yeah. So this work, the work that I'm going to talk about is based on these 3 papers, one of which is the essay that Carlos mentioned. And it's the only one that's currently on the archive. But hopefully the 2 others, with the second one being a long paper and the third one being a short version of the long paper, will be posted to the archive very soon. And it is work that is inspired by a famous paper by Feynman and Vernon called The Theory of a General Quantum System Interacting with a Linear Dissipative System. And in our case, we're going to use the results of this paper and think of the detector as the system that interacts with as a system that interacts with a bath of quantum harmonic oscillators, which will be the quantized gravitational wave. And of course, this work, we're not the first ones to use the work by Feynman and Vernon to do very interesting physics. And I should mention Beilok Hu and Esteban Calzeta, among others, who did work on open quantum systems, stochastic gravity, and in general, stochasticity and interactions between systems, between a system and a bath of quantum systems. So they have been doing work in these fields for decades. Yeah, so we are going to use basically results that have been studied by these people and apply them to a particular setting of a gravitational wave detector interacting with a gravitational wave. So the outline of my talk will be very, very straightforward. First, I'm going to talk about how we can model the essence of a gravitational wave detector. So basically, we're going to abstract a full gravitational wave interferometer, which is a complicated system. We're going to just look at one arm length. And we will consider this arm length coupled to weak gravity. And then we are going to quantize this weak gravitational field by using, in particular, by using the methods that are described in the Feynman-Vernon paper, and using the so-called influence function, that I will explain in detail. And finally, with the help of this influence functional, we're going to find the effective dynamics of the gravitational wave detector, for the gravitational wave detector. And this, a spoiler alert in some sense, this will be a Langevin-like equation for the arm length. So there will be the presence of a stochastic term. And finally, and after that, we're going to try to analyze the characteristics of this stochastic term for different initial quantum states of the gravitational wave. Okay. Yeah. So the basic idea, the heuristic idea, can be summarized in these two very cartoonish figures. That if I have two freely falling masses, and a classical gravitational wave comes by, then these two freely falling masses will oscillate in the plane transverse to the gravitational wave propagation, and so their proper distance will oscillate. But heuristically, again, our intuition says that the quantumness of the gravitational wave should induce some sort of jitters in these oscillations of the distance between the two point masses. So the whole point of this talk is to make this heuristic idea more precise, and to see if it actually corresponds to reality. I should mention here that there has been work done on this subject, in particular by Eric Verlinde and Catherine Zurek, who use holographic techniques to discuss this kind of noise given by the quantum fluctuations of the gravitational field. But in this, and this is very interesting, but in this work we will not rely on any concepts beyond those that underlie standard quantum field theory and general relativity and just basic quantum mechanics. So we will not be using any idea of holography or string theory or fancy stuff. It's just plain simple textbook physics in some sense. So very conservative. So of course, detectors, as I have said, the gravitational wave interferometers are complicated things. So they're either Earth-based detectors, such as the Virgo laboratory here, or space-based detectors, such as this cartoon of Lisa. But they all include a very kind of a universal feature, which is that they are Michelson interferometers. So they involve two or more arms, interferometer arms, that are basically just two that can be seen as two freely falling masses whose relative position is basically monitored. So this is what our detector will be. It will just model one interferometer arm. We do not actually include in our model how the actual position of the two masses, the actual relative position of the two masses is monitored, but we're just looking at the two extremities, the mirrors, if you want, of one interferometer arm of a generic gravitational wave detector. And of course, we'll couple those to gravity. So to start from very basic things, we start from this action, which is basically the Einstein-Hilbert action, with two freely falling particles. So with the action for two particles, the relativistic action for two particles, a particle of mass capital M and a particle of mass little m, each having their positions labeled by x mu and capital X mu and capital Y mu. So basically, we start from something that's very fundamental and that nobody can argue with in some sense. And then what we'll do is that we'll go into a special coordinate system. We'll pick one of these two masses to be on a reference geodesic. So in some sense, we'll neglect the dynamics of one of the two masses, and we'll only focus on the dynamics of the other one with respect to the first one. So in some sense, we're going to look at the physical separation of the two masses. So the position of the second mass with respect to the first one. And we're going to use that as our degree of freedom that will describe the detector. Okay, so if we do that, how do we, so that's the idea. So how do we make one of the particles have be on shell, have geodesic motion? So we can choose one of the two particles to be very heavy, in which case it's as if we neglect its own fluctuations around its geodesic dynamics, and then we label the other one by its Fermi normal coordinates related to the geodesic of the first particle. So by doing this, what we actually do is we lose some information, but it's information that we are not necessarily interested in. So basically, we're disregarding the dynamics of the center of mass degree of freedom in some sense, and only keeping the relative dynamics of the position of the two particles. So yeah, in Fermi normal coordinates, the positions of the two particles will be labeled in this way: T0 for the first one, which is on its geodesic, and 1 xi for the second one, and xi again being the physical separation between these two masses. So the physical arm of the interferometer. So after doing that, what we can do is expand, and what we will do is expand gravity at quadratic order in h mu nu, and go to TT gauge, and then assume small physical separation between the two masses. So small xi. So small with respect to what? Well, small with respect to the curvature scales that are relevant in the vicinity of the detectors. So this amounts to taking sort of a dipole-like approximation. It's like the dipole approximation of electromagnetism. So where we basically are not interested about in how how the gravitational field varies on scales of the order of the separation of the two particles. So in some sense, the two particles see the same gravitational field on the relevant scale of their separation. And we also take the non-relativistic limits for these two for the movement of the two particles, and then we can also expand the square roots to quadratic ordering C. Finally, we keep the lowest interacting order between H and C to get this final action for our detector interacting with the gravitational field. So this term here is well known. It's basically the quadratic Einstein-Hilbert action in TT gauge. And then we have another term, which is just the kinetic term for a free particle. So for in this case, the separation of the two extremities of the arm length. And finally, there's an interaction term, which is the important piece, which is a cubic interaction term between the gravitational perturbation Hij and the arm length, basically the separation of the two particles. So it's very important that this interaction, which is basically the lowest order interaction between these two systems, is linear in H. It's very, very important for what we'll be doing next. So I have boxed this equation because it's the equation that will allow us to go further and to actually do calculations exactly. So this will be the action for my detector, model detector, gravitational field system, in interacting detector gravitational field system. Okay, so by the way, I forgot to say, but I think it goes without saying that if you have any questions, you should feel free to interrupt me at any point. So now that we have a model for our gravitational wave detector, let's go on to look at what happens when we treat the gravitational field as a quantum field. So in general, the detector response to a quantized gravitational wave or to a quantized gravitational field will involve many, many complicated processes. So with absorption, emission, spontaneous emission, scattering. So it will be very, very complicated. But given the particular action that we have considered with this particular cubic interaction that goes like h xi squared, the only Feynman diagrams that are basically allowed in these interactions are Feynman diagrams such as these ones. So here, solid lines represent the detector degree of freedom, and wavy lines represent the gravitational field degrees of freedom. So in general, we have we start with a detector in an initial state A, and it interacts with a gravitational field in an initial quantum state psi. And those detectors are known, and things happen. And in the end, the detector is in final state B, and the gravitational field is in final state F. But the final state F of the gravitational field is in general unknown. I mean, many within the amount of time that the measurement takes place, there's lots and lots of processes that happen, and we do not measure the final state of the gravitational field. So this is very important for the following. Also, I should mention that the reason that only these kinds of Feynman diagrams are allowed is because of the particular interaction that we have, that is h xi squared. Because we have this interaction h xi squared, pure graviton loops are disallowed. And moreover, because the states will ultimately be, so technically we could have pure detector loops. But because the state will ultimately be considered, the detector is a very big object. It's an object that will be eventually treated classically. The only reason we talk about it quantumly here is because it's the easiest way to couple it to the gravitational field. But we know that in the end, it will be treated classically. So this is why we do not allow detector loops in these particular Feynman diagrams of the processes involved. Okay, so this is kind of a pictorial way of seeing what's happening when the two systems interact. And because, as I have said, the final state of the gravitational field is not measured, it means that we do not have access to that final state. So the most general thing we can look at, the quantity of interest, is the transition probability from a state A, an initial state A of the detector, to a final state B of the detector, given that there is an incoming gravitational field state psi. And of course, this happening within a time capital T. As I have said, since the final state is unknown, we need to sum over a final state to get sum over final states in order to get this, this transition probability. So the relevant formula here is this. So the probability of transition from A to B given that the gravitational field is in a state psi is the sum over F of these squares of transition amplitudes. Here, this operator U hat, which in principle we don't know yet, is the evolution operator for this coupled system. And in principle, it can be evaluated as this Feynman path integral, where S is the action for our detector gravitational field system. And I reminded you of it here. Okay, so let's try to go further. I mean, this, we haven't done anything for the moment. We're just setting things up. What if we try to evaluate this transition probability? So the first thing that we can do, and this is obvious from this expression of the action. We notice that the action has two pieces, a piece that only depends on psi, which is this one, the kinetic term for psi, and another piece that involves both the Einstein-Hilbert term and the interacting piece, so a piece that depends on H and on psi. So we can, from these path integrals here, we can pull out the purely psi-dependent piece, and then we'll get this expression for the transition probability. Of course, this is more complicated because there are wave functions in front, simple integrals over wave functions for the initial and final state of the detector, and of course, there are complicated boundary conditions here. But the general structure of this this transition probability is this. By pulling this purely psi-dependent piece out of that expression, we are left with this quantity here, which is called the influence functional, and was introduced by Feynman and Vernon in their paper, and which encodes all of the quantum effects that the quantum field Hij has on psi. So if we are able to calculate this quantity, we are already in a good position, because we know it includes all the possible quantum effects that a quantized H can have on the detector separation, on the arm length of a gravitational detector, which we model by the quantity psi. So, of course, formally, this influence functional can be read here. There's the sum, again, recall that that there was this sum over F here. So here there's the sum over F, and then there's the two path integrals over H, over the gravitational field, the gravitational perturbation H. And then the thing that appears in the argument of the exponent is the purely gravitational part of the action. What is important is that this purely gravitational part of the action is quadratic in Hij. So this means that the modes of Hij are decoupled. And moreover, it means that we can technically perform these path integrals exactly, because they're just Gaussian path integrals. And of course, I haven't mentioned it here, but the boundary conditions of this path integral involve both the initial state of the gravitational field and the final unknown state of the gravitational field that will be summed over. Okay, so we know from this expression and from the fact that the action is quadratic in H that in principle, this influence functional is exactly calculable. But it turns out that the easiest way to calculate it is not by actually performing the path integrals, but by rewriting this this expression in a canonical way. Here, the sum over F has disappeared actually, and it's written as this particular amplitude, where these particular evolution operators that should have hats, but I forgot the hats. are time evolution operators associated with the gravitational part of the action, that's SHC. So this is just, this formula is just a rewriting of the path integral formula that I just wrote. So now evaluating this influence functional comes down to evaluating this particular quantity. So to evaluate it here, so okay, this is a dangerous bend sign for those of you who know Bourbaki. But the idea, the reason I put it here is because these couple of slides will be a little bit more technical, but they're not. I tried to make them not still fairly understandable. So the first step in computing this this particular amplitude is to take the action, the gravitational part of the action, so that SHC, and decompose Hij into modes. And we can do this in the standard way. And as I have mentioned before, the modes HKS will not be coupled to each other, so they will be independent of one another. And they will, of course, involve, this expression will, of course, involve the polarization tensor, and it will be a sum over wave vectors and polarizations. And this coupling constant that appears here in the interaction term involves the Newton's constants and the reduced Planck constant. So this is a kind of a nice way to a nice expression, because it's basically just an infinite set of simple harmonic oscillators coupled to an external source. Remember, from the point of view of the influence functional, Xi is just an external source. So the path integral over Xi is outside. So from the point of view of the influence functional, Xi and Xi prime are just external sources. So they're functions of given functions of time. So we have an infinite set of simple harmonic oscillators coupled to an external source. So this should be easy to quantize, and it is. But in order to not get bogged down in minutia, we make a few simplifications. We assume that all the modes are coming along one direction, which is orthogonal to the separation between the two particles that make that are the extremities of the arm of our interferometer. And we also assume that there is a single polarization. In that case, you can rewrite this sum over modes in a simpler way, without worrying about all these polarizations, different angles, and stuff like that. Of course, this is just a simplification I mean, we could do the calculation in full generality. It's just that we'll have to worry about angles and stuff like that. So as a first step, we just look at this simplified model. So once we have this sum of simple harmonic oscillators coupled linearly to an external source, we can quantize these simple harmonic oscillators, basically quantize the theory mode by mode. So take the initial state of the gravitational field, that state capital Psi, and write it as a tensor product of states of the individual modes, which are simple harmonic oscillators. So then, very schematically, the Hamiltonian for each mode will be the Hamiltonian for the simple harmonic oscillator that does not depend on Xi, and some interaction Hamiltonian that comes from this term, H double dot Xi squared, and that will have this particular structure. It will be a sum of the annihilation and the creation operator multiplied by Xi squared. So yeah. So once we do that, and this is fairly standard, the third step and the final step is to work in interaction picture and use the Baker-Campbell-Hausdorff formula to to basically simplify these. So each one of these, for each mode, each one of these evolution operators will be something like exponential of the interaction Hamiltonian. So it will be an exponential of a plus a dagger times I squared. So the Baker-Campbell-Hausdorff formula allows us to split this exponential into an exponential of a xi squared times an exponential of a dagger xi squared times something else. And by using this formula repeatedly, what we arrive at a very important and usable formula, which writes the influence functional in this way. It's a product of all the modes of this particular amplitude for each of the modes, where we see that we are only interested in the, it's basically the square, it's not quite. So it's basically the important thing is the action of this exponential of the annihilation operator on the particular state of the particular mode we are interested in. And here the function w and f naught are known functionals of xi. So xi and xi prime, sorry. Yeah, so this formula might not look like much, but it turns out that it's the formula that allows us to explicitly calculate the this influence functional. Because, for example, you can notice here already that if I imagine that my gravitational field is in its ground state, it's in its vacuum, sorry. So it means that every mode is in its ground state. It means that there is no gravitational wave coming. It's just the quantum vacuum of the gravitational field interacting with the detector. Then this part becomes 1 because e to the a acting on the vacuum is just 1, and we're just left with this piece. So this f naught xi prime is what's called the influence functional of the vacuum, and it has a particular expression that we will discuss in the next slide. But another thing that we can do, and it's almost as simple, is to consider a classical gravitational wave. So what is a classical gravitational wave in a quantum language? In the quantum language, a classical gravitational wave is described by a quantum state, where each mode of the gravitational field is in a so-called coherent state. A coherent state is just an eigenstate of the annihilation operator. So if you replace these psi omegas by eigenstates of the annihilation operator, the only thing you'll get here is e to the w times the eigenvalue corresponding to that eigenstate. So this is what I wrote on this slide. So imagine I have a classical gravitational wave h of t coming. It means that each mode of the quantum field is in a coherent state. And then by using this formula here, this one, we get the expression for the influence functional corresponding to a classical gravitational wave propagating over the quantum vacuum. And it reads something like this, where h is the wave profile here, the classical wave profile. So h is a function, a given function of time, basically. Okay, so now let us look at the vacuum influence functional and see if we can say more about it. Well, the vacuum influence functional has an argument and a modulus. Its argument, so basically its phase, is given by this expression, where I introduced the notation x for the second derivative of xi squared. So it's kind of a complicated term that involves a second derivative of xi and third derivatives of xi and xi prime. So we'll see later that this term corresponds to, is a dissipation term, but it's not entirely clear yet. So along this, this term coming from the phase of the influence function of the vacuum is another term coming from the mod of this influence functional. And this term has this particular expression. So it's a double integral, which is quadratic in x minus x prime. And we'll see that this term actually is a fluctuation term. And we'll see that right away by noticing that this particular expression can be rewritten, again, the dangerous bend sign, can be rewritten as with the help of an auxiliary function n. So it can be rewritten as an integral, a path integral over n of t of this quantity here. So this can be seen very easily. Is basically it's pretty easy to see that you can compute this path integral over n exactly by completing the square in order to get this. But what's interesting, so this is an identity in some sense, but it's a very useful identity because what happens is that we are able to rewrite this, this term with the help of this auxiliary function n as an average, as a stochastic average over n in some sense, because this term here is a Gaussian probability distribution, a zero mean Gaussian probability distribution, which weighs the exponential of this term. So it means that every realization of n of t comes with this Gaussian weight. So in other words, n of t is a zero mean Gaussian stochastic function with autocorrelation function a of t minus t prime here, and power spectrum s of omega. The power spectrum can be constructed from the autocorrelation function as the Fourier transform of the autocorrelation function. Okay, so basically in this fluctuation term, we were able to rewrite the fluctuation term itself as a stochastic average over a new stochastic variable n, an auxiliary stochastic variable n, which we identify as a noise. So n of t will be the noise that I was talking about heuristically at the beginning of the stuff. Yeah. Okay, so putting all of this together, what we get is that we can actually rewrite with the help. So, by the way, once we reach this point, we have basically calculated we know everything. We have calculated the influence functional for the state psi exactly, and we should be able to use it to say something about the motion of the detector. So to say something about the motion of the detector, what we do is that we go back to the transition probability that we were discussing, and we plug in the expression for the influence functional that we just calculated. So here we are again in the case where the state that we're considering is a state where there's a classical gravitational wave h propagating over the vacuum, the quantum vacuum. So it's basically a field coherent state. The state psi is a coherent state. So then the transition probability is again the double path integral over xi and xi prime. Now there's an additional path integral over n, this stochastic noise. First comes the Gaussian weight, probability weight, coming for the noise n. And then comes what I call a classical piece. So basically that's formed by the kinetic term for xi and xi prime. And now the additional classical term coming from the propagation of this gravitational wave on the quantum vacuum. But finally, we have these two additional terms coming from the influence function of the vacuum, which are the dissipation term here and the fluctuation term. The reason it's a fluctuation term is made clear by the fact that it involves this stochastic noise function. Okay, so now we have a well-posed expression for the transition probability between state A and B of the detector, given that the gravitational field is initially in the state psi. What can we do to learn more about the motion of the detector? Well, what we can do is recall that when I was showing you that Feynman diagram, I said that that the detector will ultimately be treated classically, and while here it appears in a path integral, which seems to indicate that it won't be treated classically, we do think that the gravitational wave detectors are classical objects. So what we'll do is find the paths that the paths that dominate this expression of the probability of the transition probability. In other words, we'll take a stationary phase approximation for xi and xi prime. So that would give us two classical equations, coupled classical equations, one for xi and for xi and xi prime. But then we make a small leap of faith, saying that this expression will moreover be dominated by classical paths that verify xi equals xi prime. And then we get one equation, and that equation is a stochastic equation for the separation of the two masses that make our model detector. And it's a stochastic equation that generalizes, in some sense, the geodesic deviation equation. And the way it generalizes it is in the following. So, like the geodesic deviation equation, it involves the classical wave profile, H double dot here. But it also involves this new tidal force, a stochastic tidal force, which comes from the fluctuations of the quantum vacuum, this n. And finally, from that dissipation term that I introduced earlier, comes a dissipative term, which is a fifth order derivative term, which basically encodes the radiation reaction force. So this radiation reaction force is the analog, the gravitational analog of the Abraham-Lorentz force of electromagnetism. So what we have here is a Langevin style equation for the effective equation of motion of the detector in the presence of quantum effects on top of the usual classical gravitational wave description. So this is the main result, I would say, of this work. But we can say more about this noise here. About the radiation reaction term, we cannot really say more for the moment because it's a very complicated nonlinear term. But if we, for the moment, disregard this, we can say more about the characteristics of this noise. So let's look more closely at the noise. To estimate the noise, so remember, this noise, all its characteristics are well known because we know its autocorrelation function. It means that we know everything. It's a Gaussian noise. We know its mean is 0, and we know its autocorrelation function A. So it means we know everything about it. But this is not what we measure. What we measure is the effect of n on Xi. So more or less, the effect of n on Xi is to induce a variance, a stochasticity in the separation of the two masses, which is given by whose amplitude is set by its standard deviation. So here the variance can be calculated in this particular way, where xi0 is the equilibrium arm length, the separation of the two particles at equilibrium. And S is the power spectrum of the noise function n of t. Of course, technically, the standard deviation is the variance. This variance should be an integral from 0 to infinity over the power spectrum. But but that is a very divergent quantity, because we know that at high energies, high frequencies, there are new physics which probably cut off this power spectrum. But moreover, our detector, we are not sensitive to all possible frequencies. So our detector has a particular sensitivity, and that sensitivity basically cuts off this integral to a value omega max. So just a few order of magnitude figures for LIGO C0s of the order of 1 kilometer, or LISA of the order of 10 to the 6 kilometers, and the cutoff, which is set by the sensitivity of the detector, is of the order of 0.1 hertz for LISA and 1 kilohertz for LIGO. It could maybe be more, but these are some conservative estimates. So now we can look at different states and see how this variance of the noise induced on the separation of the two particles gets modified. So when we look at the vacuum or at coherent states in general, the noise is always the same. It's its power spectrum. The power spectrum of the function n of t is given by this formula. We can also do the same calculation that we did before for thermal states, and the power spectrum will be modified in this way. But we can also do it perhaps most interestingly for squeeze states, where the power spectrum will have a term of this type with an exponential enhancement in the squeezing parameter. So this is why we think squeezed states are the most promising perspectives for detecting this fundamental quantum noise of the gravitational field. Okay, so let's look at some values now. In the case of the vacuum and for classical gravitational waves propagating on the vacuum, the amplitude of this fundamental noise is tiny, despite some claims that exist in the literature that say that the quantumness of gravity has already been excluded. We can see here that this noise is sub-Planckian in size. Yeah, so it would be 10 to the minus 38 meters for LIGO and 10 to the minus 36 meters for LISA. For thermal states, things are a little bit better, in the sense that the noise gets enhanced by this factor, and the noise hovers between 10 to the minus 30 and 10 to the minus 34 meters. But it should be said that given that we are only sensitive to fairly low frequencies with our current gravitational wave detectors, detecting this particular noise wouldn't really be a smoking gun for having detected the quantum nature of gravity, because you could have a classical gravitational a background of classical gravitational waves that creates a noise that looks thermal for this range of frequencies. If we had access to higher frequencies, so if we could be sensitive to the tail of the Planck distribution, then maybe we would be in business for thermal states. But anyway, so these thermal states, I should say that so these estimates here are done for a cosmic gravitational gravitational wave background. So with a temperature of the order of 1 Kelvin, But you could technically obtain states from the thermal states from evaporating black holes, and there the temperature would be much higher potentially. However, evaporating black holes suffer from another problem, which is that they are localized objects. So this number here will get a suppression factor given by the angular, the solid angle that's subtended by that particular localized black hole. And that will arguably be very, very, very tiny. So there will be a huge distance factor suppression, unless there's a black hole that explodes right in our face. But that's very unlikely. But as I have said earlier, probably the most promising perspective of detection of this fundamental noise arises in the case of squeezed states where we have an exponential enhancement in the squeezing parameter R. So maybe I should say something about squeezed states. So squeezed states are states that are still Gaussian, but they're allowed to have an uncertainty in position or in a particular direction in phase space that is much smaller than the one usually allowed by Heisenberg uncertainty principle. The price to pay is that the orthogonal direction in phase space will have an uncertainty much larger, and therefore the overall Heisenberg uncertainty principle will not be invalidated. But what's important, so these states are used in particular in quantum optics, but in our context, they are also expected to arise as a consequence of inflation, and so as a consequence of scenarios of early universe cosmology, and which can potentially lead to large squeezing parameters. And also, very interestingly, they can also arise as nonlinear effects in binary black hole mergers. So that is also something to be investigated. For the moment, we haven't looked in a lot of detail at these possibilities, but we think that this is the most promising avenue to hope that gives hope that this particular noise will someday be detected. Okay, so I think I'm close to the end of my talk, and I'm gonna just summarize. So we introduced a model gravitational wave detector, which basically describes the interaction between an arm of a gravitational wave interferometer and quantized and the gravitational field, and we basically truncated this model at lowest interesting order, where the interaction between the two is only described by this cubic vertex h xi squared. By using the Feynman-Vernon influence functional, we ended up with a stochastic equation for the detector. So with a nonlinear Langevin equation for the separation of the two extremities of the detector. And so because it's a Langevin equation, it contained this noise term, this fundamental noise term that is tiny in principle, but can potentially be enhanced for non-coherent states. So created by sources that are that come from that have cosmological origin or from nonlinear effects in binary black hole mergers, or maybe for black hole evaporations, but I think this is less hopeful. There are a bunch of still open questions. In particular, estimating the amount of squeezing that we can realistically expect. Comparing all these noise, this fundamental noise amplitude to other characteristics of the detector, because the detector has its own imprecisions, its own sources of noise, its own systematic effects. So all of this would need to be compared to see if to basically conclude as to whether this effect is actually detectable. And perhaps very interestingly, I think this influence functional method also opens up some theoretical questions about how to properly take the semi-classical limit, how to understand radiation reaction, and maybe how to also apply these techniques to other contexts where, for the study, for example, of back reaction in cosmological contexts, or maybe even in the case of black hole evaporation. So I think that's about all I had to say. So thank you.
All right, thank you, George. I think I'm gonna clap in behalf of everybody else. Thanks for the nice talk. And then I think we can take a couple of questions if somebody has any. Let me see how this works, because I'm still an amateur with Zoom skills. Yeah, I don't see anybody raising their hands.
I'd like to ask a question.
Oh, okay, go ahead.
Hi, George. This is Ted Jacobson.
Oh, hi.
Remotely logging in. Thank you for your talk. I have a quick comment and a question, a technical question.
Mm-hmm.
Comment was about, I looked at that Zurich Verlinde work a little bit.
Yeah.
And which you just mentioned in passing at the beginning.
Mm-hmm.
And, you know, they did use holographic method to evaluate something, but fundamentally, I think they were basically taking the same attitude you are, which is just use standard known physics. They came up with a different answer, you know, very different answer. And I think their answer must be just wrong for some reason, not having to do with holography or, you know, improper invocation of string theory or something, but just an error. So that's just a comment.
Yeah, so maybe, I don't know if I should wait until the end of your...
The other thing has nothing to do with that, so sure, if you'd like to react to that comment,
yeah, so
please do.
I think we have thought about that. And one thing that... so they have this way of estimating their noise. So I think the closest our model gets to theirs is when we talk about this thermal state case. So in the thermal state case, we have a temperature which for us is a free parameter. But I think in their case, their temperature is set by some holographic considerations, and I think that is the reason why they get a much larger noise. But yeah, okay. So
well, maybe I'll communicate with you directly by email about that point later.
Okay.
The technical question is very simple. I just wonder if you could sketch like one line or something of how it is that this cubic interaction arises from the action you start with, why it has the form of c squared.
Yeah, the h double dot probably. Is that the part that, okay. Can you still see my screen?
Yes, yes.
Yeah. So if we are going to treat the second particle in Fermi normal coordinates and take the non-relativistic limit, what happens is that we can expand g mu nu in Fermi normal coordinates as well. So there will be terms of the type 1 plus r. Yeah?
Yes.
And in particular, there will be a term of the type r0ij, no, sorry, R0 I 0J times psi I psi J from the
Oh yeah, I
exponent of
see.
GPU.
Yeah. Yes,
And,
yes.
and that term, R is, so the R part of that term is the H double dot. And the psi I psi J are just psi I psi J.
Okay, perfect. Thank you.
You're welcome. Thank you for your question.
Can
All
I
right.
can
Yeah,
I
go
ask
ahead,
a
please.
naive question? So in your treatment, you have this two masses, is there an assumption that the noise in both the masses is independent? Independent?
So in some sense, I don't think so, no, because in some sense, what we do is that we fix one of our masses in some sense, and just look at the motion of the other mass with respect to the first one.
Yeah, but if the noise was completely correlated, then you would expect both of them to jitter together, right? They'd be ballroom
Yeah.
dancing.
No, I think this is noise in the tidal force. So really, he's
Yeah.
measuring the jitter of the relative separation.
Yeah, exactly. Exactly, because yeah, I think that's the only kind of gauge invariant thing that you can measure.
Okay. Malik has a chat.
Oh, he is referring to the cubic terabyte, I guess.
Does he have a question?
Malik, can you speak
No,
up?
Malik has a comment on the chat, but I think he's referring to the qubit question, qubit
I see.
interaction term.
Yeah, I think, yeah.
I have a question if nobody else has another one. Oh,
I tried to put my hand up. Did I do it right?
Oh, yes, I see your hand up. Yeah.
Okay.
oh, there you go. Yeah.
If you want to go first, Carlos, go ahead. Maybe I'll just ask mine because I hope it's brief. I have two quick questions. So first of all, maybe this is something that I should also hear offline from Ted. But do I hear you correctly, George, that you're saying that you think the reason you get a different result than the Zurich and Verlinde paper is because they're implementing holography?
So look, to be very honest, I didn't understand the way they do it very well. I'm not an expert in holography.
I think they actually do two kind of different things. So I think in their short paper, they're doing something that's not holography as deeply. In their second paper, they're really using an example of holography.
So yeah, I'm actually not sure, but when I talked to Catherine Zurek when she came to the office, my impression was that they have a particular time. I don't forget very well. I don't remember very well, but I remember that they have a procedure for setting their temperature, and
yeah,
that gives them a large temperature when in fact
the one you see is smaller.
We have no reason to take such a large temperature in our. But maybe I'm. So don't take my word for it. Because
it's possible my question is as much a question for Ted, that I'm curious as to if it isn't an issue with implementing the holographic principle. I'm curious what the difference is.
I think I'm I don't know.
Okay.
Our method is more conservative in some sense. We don't use any. We don't use any physics that is not generally accepted as being.
I could just comment maybe when I tried to understand what they had done. Up to a point, I think they got an answer that would be consistent with what you found. And then they made a sort of pirouette or something where they changed the result, trading something linear in the Planck length for something that's a geometric mean of the Planck length and the size of their region. And that step, I just failed to follow their rationale for it.
Yeah.
The temperature part per se, I don't think there was any problem with it. I think that was just a way of characterizing the fluctuations in the gravitational field using this sort of thermal description of the vacuum. But it's really just technically a different way to capture the same fluctuations you're capturing. I don't think that part really deviates fundamentally.
Okay.
I do think their second paper is more rigorous about where that trade for the geometric mean of L Planck and L comes from, but I only understand that their second paper through the holography that they're using.
Okay.
So I don't know if that means that if that step is an error, which I honestly, it seems to me like I can't find what the error is if it's there, but I also find the result surprising. The way I understand that is really through what they did in the second paper, which is holographic. So in that sense, maybe I would agree with George that their point of disagreement is coming from the implementation of something holographic.
Maybe we should start a three-way
Yeah.
email conversation.
Yeah, I think that's the right thing to do here. Sorry to take a little longer. I do have one other question though, which is what about the holometer that was at Fermilab for a while? Do you guys have any comment about that? I think you maybe made a little comment, but I don't really understand what they were doing, so I don't know what, if any, bearing it would have on what you're saying here.
So I don't know. There have been a lot of iterations of the holometer, which I don't know much about. But I do remember that at some point they were using some model where their position operators did not commute or something to get some estimate. Look, I don't really know. I don't really know. The comment I made in the presentation about claims that the quantum nature of gravity had already been excluded were related to these papers by Richard Liu from Louisiana. That estimates the noise in a very weird way. And,
okay, yeah, these are not the same papers, because I was thinking of the things from the holometer collaboration that was at Fermilab, and they, put something out about they actually had some measurements from a pair of Michelson interferometers that they claimed not to see anything.
But I think again, I think my impression, at least with the holometer, was that it was they had some particular model of non-commutative, some quantum geometry.
Yeah, that's how they were claiming to see. They were claiming to get an effect that would come from some non-commutative model, which obviously you guys aren't having to implement anything that complicated here. But they still did a measurement, and I guess I'm curious. Given the measurement they did, does that have any bearing on the results you guys see?
I don't think so, because I think their measurement is probably made to exclude whatever model they were considering, but I'm not sure. I cannot really.
Okay.
But I would be surprised if they had access to
I don't disagree. I'm just
to such good accuracy that it would have any impact on what we are saying. But
well, I certainly don't think that they were thinking about trying to prepare any kind of squeezed state, but you're talking about squeezed states that are prepared by whatever the source of the prepared by nature, not built by humans.
Yeah, exactly.
Yeah.
So I think Dan may also have raised his hand.
Yeah, can I just quickly ask, you estimate the noise term, but there's this radiation back reaction term.
Yeah.
And usually those equations have runaway solutions.
Yes.
Now, I mean, I know about these runaway solutions when there's no noise term, and then you can kind of discard those solutions. But now you have runaway solutions and you have a noise term. Is it possible that you'll always get runaway things?
So that's a good question, and I think this particular pathological form of the radiation reaction term is sort of an artifact of the fact that we're taking this semi-classical limit of a totally well-behaved path integral formula. So we're starting from this formula here, which is basically a quantum mechanical formula for the transition probability from A to B. It has no problems, no pathologies from, but then we do something to it. We take this particular approximation, and in this particular approximation, we get we get these terms that usually lead to pathologies. So one side project that we are having aims at exactly answering your question, but we haven't done much work on it. So the idea is that we assume that those runaway solutions are probably the probability of those paths is probably suppressed or something like that.
Mm-hmm.
But we haven't done much work on it yet. But by the way, this whole formalism can and even be applied to electromagnetism.
Mm-hmm.
So we can actually look at that, where the Abraham Lorentz force has a much nicer form. Well, has a nicer form. It's not.
Mm-hmm.
It doesn't have fifth order derivatives.
Okay.
But yeah, it's a good question, I think.
Thank you.
All right. Is any other question pending? I don't see raised hands. I have a sort of curiosity question. So unfortunately, I don't remember how do you build these squeeze states. But what I remember, I believe this R parameter you are using is the one that, that deviate in these states from the usual Heisenberg uncertainty principle, right? Because the mean square is just a h bar over 2 pi or something over 2. Yeah. And then this R parameter is what deviates from that behavior, isn't it?
Mm-hmm.
So on physical grounds, do we expect that parameter to be large? I mean, it's on physical ground. Is it? I mean, this parameter is bounded somehow because I'm thinking that going farther away from the usual mean square of an operator can be hard to do. But it's just
So
naive intuition.
So in general, yeah, that's we haven't done very precise work on this, but in general, there are two ways that you can think of these squeeze states being created. One would be if you have nonlinear effects in gravity. So if at the source you have interactions of the type JH squared. Yeah. Mm-hmm. So imagine you have a classical source J. Mm-hmm. Interacting with creating a gravitational field via this particular interaction JH squared. Mm-hmm. So there you create a squeeze state. Mm-hmm. So in principle, the squeezing parameter will depend on J, on the way J behaves. Yeah. So
J being a coupling.
J being a classical source. Imagine, I don't know. Something where gravity is strong enough to not neglect the h squared term.
But in that case, then
so there
you have to consider the nonlinear effects.
Yeah, exactly. So this is a nonlinear effect. H squared j would be a nonlinear effect.
Okay, but aren't your equations at linear order? Because you start with an action which are linear order.
No, my equations. I'm working at the level of the detector. Yeah. So, but if my state, so separately from my detector, my state is created somewhere far away. Yeah. And it may be created in an area where gravity is strong or stronger. And there you might have an interaction of the type JH squared.
I see. Yeah.
There you would get a squeeze state. So, and the squeezing will depend on the characteristics of J.
I see.
Cosmologically, it can arise from inflation and from basically a mismatch of vacua. But, and there, I guess, but okay, full disclosure, the squeezing parameter, the way we estimated, these formulas that I gave are valid for a uniform squeezing parameter, where each mode is squeezed in the same amount, which is not true in cosmology, for example. It wouldn't be true in the JH squared case that I just talked about. So basically, each mode will be squeezed differently, and that depends on how that mode behaves in the early universe and stuff like that.
Okay.
But yeah, it's probably it's related to basically the number of e-folds.
Oh, okay.
Yeah. But it's very. But what I wanted to say is that the omega dependence of the squeezing parameter is very important, because yeah. Anyway.
Okay. All right. Thank you. So I think it's a good time to end the talk. So thank you very much. I'm still clapping for everybody else. And I don't know if there are people interested in staying